Good morning, guys. Um, I hope you're doing all right. Yesterday, I went to the grocery store and it was an incredibly stressful 3 hours going to two stores and the dry cleaners. It is crazy how simple things have become so stress inducing. But hopefully, you guys are doing all right. Um, And as a reminder, there is a homework assignment that is due today. Um, if you haven't gotten that in, make sure that you do that. There's also the first part of a homework assignment that's going to be due next week. That's posted. Some more problems will get added to it today. Um, but I guess let's get going. In place. Okay. So as a reminder, I don't know if this was up last time, but it is now. There are some YouTube links to these lectures, so you can see everything that we're talking about. If you need to go back and review them, it is still important to be here, asking questions and kind of making sure you understand things in real time. Um, Also, the lecture notes, which are going to be putting up. Uh, it's a little annoying to get all the pictures in one file, but I'll keep figuring it out and keep posting them. Okay. So as a brief recap of where we were last time, we were introducing really some new types of objects that we're talking about. So the first was ordered pairs and Cartesian products, which are sets of ordered pairs. So for any sets A and B, we can form their product, which is just take all ordered pairs where the first coordinate comes from A and the second coordinate comes from B. But more often, we aren't interested in looking at all pairs coming from two sets. And we really want to look at a relation, which is a subset. So a relation consists of pairs coming from A and B, but it's not all of them, it's just a particular subset. And as some extra terminology and notation, if it's the same set, so if our R is a relation from A to A, then we'll just say that R is a relation on A. So it's not relating things from A to B, but it's relating things in A to other things in A. So we'll say it's a relation on that set A, where all of the things being related are coming from. Some other notation, which I won't always use, but sometimes I might, and I just want to make us aware of it, is that instead of saying that an ordered pair is in R, so R is a set of ordered pairs, which means ordered pairs can be in it or not in it. Sometimes we'll write R in the middle, so we'll say X is R related to Y. So this notation makes it look more like x less than or equal to y. So here, less than or equal to is a relation. It's some way of relating real numbers to other real numbers, and you can think of it as a set of ordered pairs. But we don't write something like x, y is an element of less than or equal to. We have it in the middle of them, kind of showing that they're related in a certain way. So sometimes we'll use this notation too, not always, but just so you aren't totally lost when you see that. Okay. So some small examples. First, let's just look at a finite set or a finite relation. So if we take two sets, A is 0, 1, 2, B is 2, 4, 6. These are two sets. We can form their Cartesian product. I won't write it out, but if you find the product of A times B, you'll have 9 ordered pairs. So it's a 0 with all 3, 1 with all 3, 2 with all 3 of them. So we get 9 of these pairs. Then we can write down a relation, and actually in this case we'll explicitly write out what the pairs are. So R is this set with the 3 ordered pairs in it, 0, 2, 2, 2, and 0, 6. So this is a relation from A to B. All the first coordinates come from A, all the second coordinates come from B. And from this kind of writing the relation explicitly out, writing out exactly what ordered pairs there are, we can tell when things are related. So 0 is related to 2, 2 is related to 2, and 0 is related to 6, because we can look and see that those ordered pairs are actually in the relation. But 1 is not related to 2. So just like writing not equal to or not less than, we put a line through this R telling us that these two aren't related, because the ordered pair 1, 2 isn't on this list. It's not an element of the relation, and so 1 and 2 aren't related to each other. We can also, if we want, write this using some of our logical notation and say that the statement 1 is related to 2 is false with this negation in front of it. So these finite relations are good for getting a handle and being able to see everything that's related to everything else and getting a feel for what kind of different, as we talk about relations, they're good examples because we can really see everything about them. More often, relations are given by some property that we spell out, but we can't just write out all the pairs. So for instance, we can define a relation P on the set of natural numbers by saying X is P related to Y. So that means that the pair X, Y is in the relation P. And two things are related if and only if X is a prime factor of Y. So for instance, 3 is related to 6 because 3 is a prime factor of 6. 6 is 2 times 3. 3 shows up in that prime factorization. 5 is related to 20 because 5 shows up in the prime factorization of 20. 4 is not related to 12. And here we need to be careful about exactly what the relation is telling us. 4 is a factor of 12, but this is saying it has to be a prime factor. So we're only looking at the prime factorization, and 4 isn't prime. Also, 3 isn't related to 7 because 3 just isn't a factor of 7 at all. So given this relation, we can write down, or we can use the definition to figure out when two pairs of numbers, since that's the set on which our relation lives, we can figure out, or we can decide when two numbers are related or not related. But there are other questions we can ask besides just write out all the pairs in the relation if it's finite like this, or determine whether pairs are related or not. So for instance, and I'll give you guys a chance to think about this for a second before I sort of scroll up and reveal it. For this relation P on the set of natural numbers, we can write down these two sets. The set of natural numbers x, so 2 is related to x, and the set of x in the natural numbers, so x is related to 18. Now, one thing that's important is that the order matters here. So in the way that this relation is defined, x is a prime factor of y. So in this case, what this is saying is find the x's, so 2 is a prime factor of x. And this one is saying find the x, so x is a prime factor of 18. So when we're deciding what property we're really looking at, the relation has these two variables, x and y, and here we filled one of them in, so these are properties that just have one variable in them. So these won't be pairs, or the sets that we come up with won't be sets of pairs. These are just particular numbers which are related in some way to 2 or 18. And if we write out what these are supposed to be, the numbers, so 2 is a prime factor of x. Well, 2 is prime, so if it's a factor at all, it's a prime factor. But then describing the x that have 2 as a factor, those are exactly the even numbers. And we can write that in the way that we've written even numbers before. The set of x that look like 2 times m for some number m. The other set is asking a very different question. It's saying which x's are related to 18, and this is saying which x's are prime factors of 18. So here we want to look at 18, find its prime factorization. 18 is 2 times 9, so that's 2 times 3 squared. The only prime numbers that show up in its prime factorization are 2 and 3. So one thing with relations that we really need to be aware of is the order that in which things are related matters. So if you wrote in this case, let me see if I can, if we changed this to find the x which are p related to 2, this is asking a very different question. It's asking a question similar to the second example. What are the prime, find the x's which are prime factors of 2. In that case, there's only one prime factor, and that's actually just, I'm making these curly brackets with the pen they give you is difficult. So if we want to find the x's which are prime factors of 2, that gives us just the number 2. Written the other way, find the numbers that 2 is related to x, that gives us all the even numbers. So the order in which things are related matters. What can also be helpful is that we can sometimes graphically represent relations. So if we go back to our first relation, our finite one, where we have these two finite sets, and we pick out a couple pairs that are going to be numbers related to each other, we can represent that by saying A was 0, 1, 2, B was 2, 4, 6, and a line from A to B says this number is related to this number. So this element of A is related to this element of B, and that each line corresponds to a pair in the relation. So this picture says 0 is related to 2, 0 is also related to 6, and then 2 is related to 2. And if you look up at the pair, that is exactly the pairs that we wrote down. So these pictures don't work quite as well for relations like this, which are infinite, and we'd have a lot of lines to draw. But for finite ones, where we can actually know what all the related pairs are, it's really nice to give a kind of graphical representation. Okay. So this is a recap of the relations we were talking about last time. Are there any questions before we start seeing some really new material? Okay. Okay. So given relations, we were talking about what questions can we ask about them. We also want to figure out what are some sets that are relevant for a given relation. And these definitions we'll introduce, you've heard them before in the context of functions. And that is a helpful way of thinking about them, but we'll also want to be careful that we're using them in the way we're introducing them now. So we'll start off, let R be a relation from A to B. So this means that R is a set of ordered pairs, and it's a subset of A times B. The domain of this relation R is going to be the set of first coordinates. Written out, the domain of R, and this is the notation that we'll use. The domain of R is the set of all elements A in capital A. So all of the elements in the first sets in our product. So there's some B in B. So A comma B is a pair in R. So another way of thinking about the domain is they're the elements in A that are related to something in B. Which means, as we kind of said at first, these are all possible first coordinates for any ordered pair in the relation. So it can happen that an A might be related to a lot of different things in B, which is fine, but all we're really thinking about the domain is if you're related to at least one thing. But also, if you're an element of A which happens to just not be related to anything, then you're not going to be in the domain. Really similarly, but moving to the other half of the product, the range of R is going to be the elements of B. So there's some A in the first part of the product, capital A, so AB is in the relation R. So the range is a set of all second coordinates of ordered pairs in the relation. They're the B's, so there's something in A which is related to B. And again, there could be a lot of things in A related to that relate to a single B, but we just need one of them. But if there's some B which isn't related to anything in A, that won't be in the range. What we'll also be talking some about is the inverse of a relation. So for some relation R, its inverse, so R is a relation from A to B. Sorry, there's an ambulance and a fire truck that just went by. So we're interested in the inverse relation. So R is a relation from A to B. Its ordered pairs look like something in A and something in B. R inverse is essentially flip everything in R around. So R inverse will be a relation from B to A. So it's changing which of the sets gives you first coordinates and which one gives you the second coordinates. And R inverse is all the pairs, so if you flip them, you get something in R. And we can also think about this as take all the pairs in R, flip the order, so the B element comes first and the A element comes second, and all of those flipped pairs, that makes up R inverse. So for example, let's look at our finite small relation. So 0, 2, 2, 2, 0, 6 from the set 0, 1, 2 to the set B 2, 4, 6. So the domain is anything that appears as a first coordinate. And so we get 0 and 2 and 0 again. The fact that 0 appears twice doesn't really change what the domain is. It just shows up on our list twice. So the domain is just 0 and 2. Those are the only first coordinates that appear in R. And so 0, 2 is a subset of A. The domain is a subset of the first half of the product that the relation R lives on. But in this case, it's not everything. 1 is in the set A, but since it doesn't appear as a first coordinate, it's not in the domain. A similar process can show us that if we talk about the range, these are all the second coordinates. We get 2 and 2 again, so that's nothing new, but then 6. So the range is just 2 and 6. And again, there's this middle element of the set B isn't in there. 4, while it's in B, it's not actually a second coordinate for this relation, so it's not in the range. And the inverse is, going back to our ordered pairs here, take all of these ordered pairs and now flip them. So 0, 2 becomes 2, 0. 2, 2 doesn't change because it's the same number twice, but 0, 6 flips to 6, 0. And now this is a relation from B to A, because these first coordinates, 2 and 6, come from this set B, and the second coordinates, 0 and 2, those now come from A. So for these small relations, we can see exactly what the domain and range are, and explicitly write out the inverse. But in a lot of cases, the inverse is an interesting relation on its own, especially if our initial relation is a kind of naturally occurring one. So for instance, the less than relation, which we'll say L to give it a letter, is the set of XY pairs in the XY plane. So it's in R times R. Take all the pairs, so X is less than Y. That's relation on the set R. So for this set, the domain and range are actually all of R. Given any X, it is less than some Y. So every real number X appears as a first coordinate. And also, every Y appears as a second coordinate. For any real number Y, there's some X, so X is less than Y. Okay. As a comparison, just to see that this isn't, like this is actually saying something. What happens if we think about this less than relation on N, on the set of natural numbers? So still using X is less than Y. So in this case, the domain writing that this is tough. The domain is everything. Why is this? This is because every natural number appears as a second coordinate. Given any number, any natural number, it is less than something. So given any natural number n, you could say n comma n plus 1 appears in the relation. But where things get different and why we need to be careful about this is that the range is natural numbers except for 0. So why is that? The range is anything which appears as a second coordinate, which means which numbers have something less than them. So which numbers are able to be in a pair xy where x is strictly less than y. And in this case, there is no natural number, so you can say that it is less than 0. So you won't be able to, if you're only looking at natural numbers, you can't find a pair that looks like something comma 0, because that would mean you have a natural number less than 0, and there just isn't one. So even with kind of the same definition, depending on which set you're living on, that can change properties of the set. In this case, it's changing the domain is kind of the same, it's the whole set, but the range can change. And for this relation, if we talk about its inverse, that's saying the original relation is all pairs xy, so x is less than y. The inverse is find all pairs which are the reverses of pairs in here. So if you have two numbers x, y, and they're in here, that means x is less than y. The inverse is going to have that pair in reverse, y comma x. And this is another natural seeming relation. The inverse of the less than relation is the greater than relation. Because if you have two numbers that are related one way, and you think of it, one as being less than the other, reversing the pair tells you that the first one is greater than the second one. Questions about either of these examples? Something that I can say to clarify any of this? Okay. Let me click that. So to do one, or I guess to kind of finish the examples that we've been introducing, we introduced this relation P, which has all the pairs of natural numbers, x, y, so x is a prime factor of y. So in this case, let's think about what the domain and range are. So if we take all pairs x, y, so x is a prime factor of y, what are the possible first coordinates? Well, if you're going to be a first coordinate, you are the prime factor of something, so you definitely have to be prime. We at least need to have those in there. Or I guess that's not right. So what I want to say is to be in there, you have to be prime. If you're composite, you are definitely not a prime factor of anything. But also, every prime does appear as a first coordinate. In particular, every prime number is a prime factor of itself. So given any prime number, 2 or 5 or 31, those all appear as first coordinates because you'd say 2, 2 is in here. 2 is a prime factor of 2, so 2 appears as the first coordinate, and so it shows up in the domain. So the domain in this case is all prime numbers. And if you were to write down a careful proof of this, there would be really two halves of this to prove. You'd have to say, if you're in the domain, you are prime. So the domain is a subset of this set. And that would be something like, if you're in the domain, you are the prime factor of some number, which means you have to be prime. And the other direction says, if you are prime, you'd have to come up with the ordered pair, which shows that you actually appear as a first coordinate. So there you really have to actually write down, here's an ordered, or you start with a prime number, then you write down, here's the ordered pair that has my prime number that I was starting with as a first coordinate. And as the other half of this, the range, this uses the fact that really every prime number or every natural number greater than or equal to 2 has a prime factor. We can always break it apart into, we can form the prime factorization, split it apart into smaller and smaller numbers until we get to primes, which we can't split up anymore. And as kind of conventions, 0 and 1 don't really have prime factors. But every number then 2 has a prime factor, so every number 2 appears as a second coordinate. And depending on the prime factorization, it might have a lot of prime factors and might appear as a second coordinate in multiple ordered pairs. But all we need is for it to have 1. Okay. Questions about any of these examples or just the sort of concepts introduced here? Okay. So let's talk about what some proofs involving these relations look like. So in the textbook, there's a theorem, theorem 4.25, establishing some basic relation facts. So it says that for a relation from A to B, the inverse of R inverse is R, the relation you started with again. The domain of the inverse is the range of the original relation, and the range of the inverse is the domain of the original relation. So these facts, if they seem familiar, you've likely encountered them when you were talking about inverse functions. So the fact that these are true is maybe not surprising, but how we actually show them, we'll want to be more careful about. So I'll prove A and C. B is in the textbook, so you can read that there. But it would also be, I think, after seeing what the proof of C looks like, maybe try to prove B by yourself and then compare it to what's in the textbook as a check of how well you understand these proofs involving relations. So with A, if you were doing some scratch work ahead of time, the thought process would be, well, this inverse thing flips the order of all the ordered pairs. And the insight is 1 going from R to R inverse flips them one way, going from R inverse to its inverse flips them back, but then you're in the original order, which was R. So that's the nugget of insight that we need, but what we want to be careful about is how do we actually write that out? So one observation which is good when you're talking about relations is show that they are at least the right kind of objects. So in particular, R is a relation from A to B, and R inverse is a relation from B to A. So taking the inverse of that flips the two halves of the product. So R inverse inverse is again a relation from A to B. So that says that at least they have a chance of being equal. If you have two relations that are relations on different sets, there's no way that they're equal. If you have, if you have R as a relation from A to B, and another relation is a relation from like B to a third set C, those are really just kind of the wrong types of objects to really be equal to each other. So this says we're living on the same sets, so the fact that they're equal is, there's not something obviously wrong with that statement. So what we can say is they're living on the same set. Let's take one of these ordered pairs. And in this case, we'll have a fairly streamlined proof, which is saying two sets are equal if being in one set is equivalent to being in the other set. For any set, for any object of the right type. So for any ordered pair, a little a b from capital A times b, if it is in the relation R, by the definition of inverse, that means that the flipped ordered pair is in R inverse. So that's just what the inverse means. But then we can repeat that flip by saying, if we go from this relation, forgetting about what it looks like, but saying we have a relation here and an ordered pair in it, if this ordered pair is in this relation, then if we flip the ordered pair, we end up in the inverse relation. But then what we've established is this ordered pair AB, being in the relation R, is equivalent to that same ordered pair AB being in the inverse of R inverse. And so for any object or any pair AB in A times B, you're in R if and only if you are in R inverse inverse. And that means that these two sets have exactly the same elements. And where you might, if you were working with this proof for the first time, what you might see in your Scratch work is we're trying to show two sets are equal. We do that by showing one is a subset of the other. And what would be there, and it would be there if you were able to notice it, is that if you wanted to show that just half of this, that R is a subset of R inverse inverse, which is half of the process of showing that two things are equal, what you would get would be this left to right direction. You would say start with something in R, flip it to get to R inverse, flip it again to R inverse inverse. This left to right direction shows that R is a subset of R inverse inverse. But after you write that out, what you can look for, and this won't always happen, but it's happens enough that it's something you can try to look for, is that that reasoning is totally reversible. So that means that if you wanted to show the other subset containment, so that R inverse inverse is a subset of R, then how that proof would go would be you have an ordered pair, it's R inverse inverse. If you're going from an inverse of something to the original something, you flip the ordered pairs. So then if the ordered pair is in the inverse inverse, the reverse of the ordered pair is in just the normal inverse. But then you can flip it back to go from R inverse to just R. So the right to left direction here is actually showing that R inverse inverse is a subset of R. And if when you write out a proof, you see that the steps of showing one set as a subset of the other set, if those steps are completely reversible, then how the eventual proof can be written is as just equivalent statements. This object being in this set is equivalent to this object being in this set, is equivalent to this object being in this set. And if you have a string of equivalences, then that means the first statement you wrote is equivalent to the last one. And in this case, that shows being in R is equivalent to being in R inverse inverse, and that means that those sets are equal. Okay. So the proof here is very short, but the thought process that goes into it is there might be a lot more scratch work, and then you just kind of notice, oh, hey, these two halves are the same steps but in reverse, and then it can write those as a string of equivalences rather than one directional in trying to show that one is a subset of the other. So we can do the same kind of reasoning for part C, or the proof will be, again, a string of equivalences, but we'll actually talk a little bit more about what the scratch work is going to look like. So C, what we're proving, I can get that on there, is that the domain of R is the range of R inverse. Okay. So first, figure out why this is true and what steps we might want to take along the way. Is that the domain of R, by how it's defined, is all first coordinates in the set or in the relation R. And the definition of the range of R inverse is all second coordinates in the relation R inverse. And then how these things will be connected is that if a pair is in the relation R, then its reverse is in its inverse. So how we can piece these together is if you take a first coordinate in R, then it appears in an ordered pair. You can flip it to get an ordered pair in the inverse relation, but then after flipping it, this X is, which was a first coordinate over here, so it's in the domain, is a second coordinate over here, so that means it's in the range of the inverse. So those are the steps that we're going to be using. And when writing out this proof, we want to show that being in one set is equivalent to being in the other set. And again, if your scratch work, what you do is show that one set is a subset of the other, what you will notice is that for the kind of proof I imagine you would write out, is that all the steps are reversible, and rather than showing it as two instances of one set as a subset of the other one, you can show it as a string of equivalences, and then show that being in one set is equivalent to being in the other set. So for any A in A, well, first we can kind of establish that these sets are in the right place, so they have a chance of being equal. So the domain of R is a relation from A to B, so the domain is a subset of that first set A. And then the range of R inverse is a relation from B to A, so the range is a subset of that second set A. So they're at least both subsets of A, which means we're in the right place, so we have a chance of them being equal. So then they're both living in A, look at elements of A, and then figure out what does it mean, or if we assume that A is in the domain of R, how can we unpack that? So we're unpacking this definition in the same sense that if we said, here's a number that's even, write it as 2 times something. So we have this defined notion, the domain, rewrite it without that defined notion, and that gives us more stuff to work with. In this case, we're saying if A is in the domain of R, then it's a first coordinate. So that means we can say, here's a pair that has that first coordinate A. So if A is in the domain, that is equivalent to the ordered pair AB being in the relation for some B. So you can find a B in capital B. So the pair AB is in the relation. That's what it means to be in the domain. But then from here, how we know a relation and its inverse are related is that if this pair is in R, then that means that the pair BA is in R inverse for some B in B. But now what we know is that this A that we're really keeping track of the A, the B appears because if we're talking about ordered pairs, there has to be this second point appearing. But we're really keeping track of A. And if we have this statement here, that BA is in R inverse for some B in B, that means that A appears as the second coordinate of some ordered pair in R inverse, which is exactly what it means for this A to be in the range of R inverse. And so if you were just going kind of left to right, this would show that the domain of R is a subset of the range of R inverse, but each of these steps is reversible. If we know that you're in the range of R inverse, you're the second coordinate of something in R inverse, which means you're the first coordinate of something in R, which is exactly what it means to be in the domain. Okay. Questions about anything? Any of these proofs? Okay. So one idea to keep in mind in all of these is when you're talking about relations, really all of the work is, a big step is you need to going between elements and ordered pairs. So we're really talking about kind of element coordinate level here, but how we learn about that is that we talk about the ordered pairs in there. So one other topic, which you likely recognize from talking about functions, is talking about composition. So we can compose relations also, and this picture in particular is a common graphic when used about talking about composition of functions. So in composition of relations, what we're saying is we're taking two relations and we want to combine them in some way to form a new relation. So what we're starting with is some relation R as a subset of A times B. So R is a relation from A to B. And then there's a second relation, which is a relation from B to C. So what's important is that you have two relations, but the second set in the product of R is the first set in the product that S lives on. And if we have that set up, two relations that kind of share this common set, then the composition, this circle isn't multiplying, it's a little open circle. S composed with R is a new relation that's from the first set in R to the second set in S. So the set they have in common, B, isn't in the equation anymore. There aren't going to be elements from B in the final ordered pairs we're looking at. But B is still important for this. So the composition is a relation from A to C, and what the composition looks like is it is pairs AC coming from A times C, where there is some B, some single element B from the middle set, capital B. So you can go from the first coordinate A to that B, but then from that B, you can take one more step to end at the final set C. So the composition is really what pairs can you get from A and C, where you can get from that A in A to that C in C by taking a step, or rather two steps, through some single element in B. So let's look at an example of this. Okay. So here's one composition. Let's say and in this case, the picture representation is really helpful. You could also get this information from the sets of ordered pairs. I didn't feel like writing out the sets of ordered pairs because there'd be, because the pictures do, I think, a better job. But you can also look for this or figure this out if you're just using sets of ordered pairs. So here we have two relations. R is a relation from A to B, and it has these arrows as the things in A related to things in B. And S is a relation from B to C, where the B in it, that's its first set, is the same as the B from the second set. And the arrows say which elements of B are related to which elements of C. So how we find the composition, and we can do that because they share this middle set. A goes into B, S goes from B to a third set C. So the composition is going to be pairs that look like some A, comma some C, where we can go from this A to some B in the middle, and then to the C in the pair. So the picture we get is the combination of these arrows from A to B, and then these arrows from B to C to give us this two-step process. And what we're looking for is, what are the pairs where we can start in A and end in C by using the appropriate arrows? So at first, if we start at A1, it has an arrow to B1, and that has an arrow to C1. So that path is going from A to B to C. And so the starting and ending points, that's a pair in the composition. So the pair A1C1 is in the composition because we went A1, B1, C1. And A and C are the pairs we're looking at. So the B is the stepping stone in the middle, but that doesn't appear in the pair in the composition. We can get another pair by saying A1 also goes to B4, and that continues on to C3. So with that two-step process from A to some element of B to some third element in C, the starting and ending point, those elements form the pair in the composition. If we keep looking, we say, well, hey, A2 goes to B3, but there's no arrow going out of B3. So that doesn't end up giving us a pair. Also, there's an arrow going from B2 into or to C2 and to C3, but there's no way to get from anything in A to B2, so we can't get an arrow that way. So when we're looking for these pairs in the composition, it has to be this two-step process. And sometimes the arrows only get us halfway, and those don't give us pairs in the composition. Questions about this example? Or the idea of composition? So we'll say that in the textbook, it has a lot of examples of composition. The ones in the textbook are kind of non-mathematical. So I decided to not spend really time on them. But if you want to get more of a feel for how composition works, there is a lot of material in the textbook, and I recommend looking at it. And the textbook has a lot of material, so you don't have to look at all of it, but if you can read a few examples and it starts to make things click that are not yet clicking, it would definitely be worth the time investment. Okay. So what if for these two relations, what if we combined this composition with inverses? So this is where a board would be nice, but let me kind of zoom out a little bit. Okay, so what is R inverse S inverse? So combining this composition with inverses. So if you have a relation R, then what the picture of the inverse relation looks like is really just taking these arrows and turning them around. So you'd go from B1 to A1, B3 to A2, B4 to A1. That's the picture of the inverse. Similarly with S1, you turn all these arrows around, and so you're going from elements of C to elements of B. And so putting them together, and yeah, even when putting them together, you still are turning the arrows around, but you also have a different starting point. So this R inverse composed with S inverse, how we figure out what it's saying is, well, S inverse goes from C to B, R inverse goes from B to A, so the composition, this picture says, would go from C through B in the middle, but ends at A. And what we try to figure out here, or to try to figure out what relation this actually is we're looking for pairs now C comma A, the first coordinate from C, the second one from A. So we again have this middle step. We're going from C and see what is related by S inverse to something in B. And then from that stepping stone, what is that related to by R inverse to things in A? So this picture is this first picture of the composition, but not only are the arrows flipped, but we've kind of moved the last set C over to the left and the first set A over to the right. But once we have this picture, we can still ask the same question. What two-step processes can we make here? So we have C1 goes to B1, goes to A1. So that gives us a pair here. C2 goes to B2, but that dies. C3 goes to B2, but that dies. C3 goes to B4, and that continues on to A1. So we get C3A1. And then this last arrow we haven't talked on makes it into A, but there's no way to get there from C, so this doesn't give us any pair. So we have this composition with these inverses. We still have to do some work to figure out exactly what relation it is, but we can still compute what this composition is. And looking at these two examples, if you're happen to notice it, you see something kind of funny. The original composition had two pairs. The inverse of these compositions has two pairs, and the pairs are just flipped. So A1, C1 is in the original composition. This composition with inverses in a different order has C1, A1, and then the A1, C3 from the original composition is flipped to become C3A1 in this composition. So another way of saying this is that this relation that we computed is the inverse of this actually first relation that we computed. Because we've taken the two ordered pairs in here and flipped the order of both coordinates to get these ordered pairs down here. And this is not an accident. Okay. Right. Sorry. I need some. My computer needs some battery. My wife is helping me out. Okay. So this fact is kind of surprising that it happens to work out this way. But in fact, this is a really general relationship of how composition and inverses interact. So this is actually the second part of theorem 4.2.5. It has some facts about composition. One of the pieces that we aren't talking about here, but they do part of in the textbook, is that composition is associative. So if you have three relations going from one set, or if you have three relations and you're composing them, there are kind of two different orders in which you can do the composition, do the first two and then the third one, or do the second two and then put the first one before it. And you get the same relation in any case. So I suggest taking a look at that theorem. It walks you through that or part of that result and leaves this as an exercise. So I'm kind of filling in the gaps or some of the gap that they leave, and the textbook is taking one of the results that I'm not going to talk about. But what we will get a feel for, which is helpful when you go to look at that other theorem, is what do proofs look like involving composition? So the general theorem that is true is that if you have a relation from A to B and a second relation S from B to C, that if you compose them and then take an inverse, that is the same as taking the inverse and then composing them in the reverse order. So we saw a specific case of that happening in the last example, but in fact, any relations at all, even if you can't write down the ordered pairs or make the picture, it's still behaving in that way. So what we'll focus on is just showing one of the directions. And showing that these two relations are equal will show that the left one is a subset of the right one. But after we're done, we'll have understood enough of them that going the other direction you should be able to do. Okay, so first let's think about what's going on. In this one, there's a lot of stuff, so we're definitely not just going to dive into the proof. So first up is this quick kind of sanity check, I guess you could say, that they're at least living on the right sets. So given our relations here, S composed with R is a relation from A to C. That's how the composition works. You start with something in A, you go through B, but the second coordinate comes from the last set C. So S composed with A is a relation from A to C. So when we take its inverse, we flip the two sets in the product. So the inverse is a relation from C to A. Okay. If we look at them, the two relations individually and take their inverse first, well, R goes from A to B. So our inverse goes from B to A. And then S goes from B to C. And so its inverse goes from C to B. So we can compose these, but now we see we have to do it in the opposite order. S inverse goes first, and that goes from C to B. And then our inverse goes second, and that takes us from B to the final set A. So this composition, we start with something in C, S inverse relates that to B, then R inverse takes over and relates that to something in A. So this composition, again, is from C to A, so it's the right set. And so they're at least living on the right sets, so we can try to show that they're equal. Okay. So we have the eventual proof here, but let's focus on the kind of scratch work here. So what does it mean if we're trying to show this subset relationship? So it means we are starting with an ordered pair in this relation, which looks like something in C related to something in A, and we want to end up with it being in this relation here. So to get there, what we need to use is, if we know something is in an inverse, what else do we know? And if we know something is in a composition, what does that mean? So what we can say, or the kind of steps we can see, and we'll write it out more carefully after we figure out what the steps are going to be. So if CA is in S composed with R inverse, then if we flip the order of the pair, we end up in the original composition S composed with R. So that's using what it means to be in an inverse. But then what we do is that if you're in a composition, that really means that there are two pairs you know exist. There's some new element B that shows up in them. So if AC is in a composition, that means that there's some third element B in capital B. So AB is in R, A the first coordinate from the ordered pair we're talking about, B this new element, that is in the relation R, and then BC is in S, B the new element, C the second coordinate from our original ordered pair. So if we know that a pair is in a composition, then that means we know that two other pairs exist that are in the two composed relations, and they share this common element in the middle. Okay. So that really breaks it down to now we know about these ordered pairs being in these relations. And at that point, you're maybe not sure exactly what to do. And so, what we can, or a strategy that we can use is, what if we try to reverse engineer how would we end up over here with our goal? We want to show that this ordered pair CA is in this relation S inverse composed with, or R inverse composed with S inverse. So in this case, the composition is happening first. We have this relation, it happens to be an inverse. This relation also happens to be an inverse, but we're composing them together. So then, like before, that means we know that there are two ordered pairs that exist containing some element B from this middle set B. And it's the C that was our first coordinate, and B that was introduced is in S inverse, the first set. And then the B that was introduced in A, our second coordinate, are in the second relation R inverse. And that gets us to the ordered pairs. But then where we can see how these pieces actually connect is that over here we had this pair AB is in R, this pair BC is in S. And if we flip these pairs around, we get exactly the pairs that we wanted to be in these inverse relations. So as a strategy for coming up with these proofs, it can work to start at where we are starting, get as far as we can, and then also look at where we want to end up, kind of reverse how we could get there. And then somewhere in the middle, hopefully we can link these two up. And so what our proof will look like is really writing in a linear fashion this sort of U which appears here. But all of the steps, or we've laid out the logical steps that we're going to take, we just have to write it out in a linear, kind of coherent way. So what can this proof look like? So first, establishing that these relations are on the right sets. So they're the right kinds of relations to actually be equal to each other. And given that we're trying to prove that the left relation is a subset of the right relation, that means we start with an ordered pair from this relation. And then keeping in mind we laid out the steps that we want, that means if this ordered pair CA is in the inverse of S composed with R, then the flipped ordered pair is in the normal composition of S and R. But then we said that if this ordered pair AC is in a composition, that there's some new element B. So A and this B are related. The ordered pair AB is in R. And the second numbers, or the second coordinate C and this number B are related in S, that B comma C is in the relation S. But then we saw what we need to do with these is we need to turn them around. So since AB is in R, its reversal is in R inverse. And since BC is in S, its reversal is in S inverse. But then what we see here is that we have two ordered pairs which have the same, or have this common coordinate, the second coordinate here and the first coordinate here. So that means that if we take the first coordinate here and the second coordinate here and put those together, that gives us an ordered pair in the composition. So because we know there is a B, so CB is in S inverse and BA is in R inverse, then we can take the first coordinate and the second coordinate and put them together to get a pair in the composition. And that was where we wanted to get to. We started with a pair in S composed with R inverse, and we showed that that pair is in R inverse composed with S inverse. And as a last comment, it'll be a good exercise to write a proof for the other direction, but either in our scratch work here or as we were laying out the proof, what you can notice is that these steps are really reversible. If you started with a pair in R inverse composed with S inverse, you can back up through these steps that we established and really get that if a pair is in this composition, it's in S composed with R inverse also. So as an exercise, you can try writing out a complete proof, but we really have the logical steps here. We just want to talk about what does that actually look like when we write it out. So this could be another proof where we have a string of equivalences, but in this case, it's, I'd say, significantly more complicated. So trying to more carefully lay out why these things are true rather than just equivalent, equivalent, equivalent can be a good idea. Okay. So that takes us to the end. What we're going to do next time is there's some more pictures that can be associated with relations to help us understand them, but also they can give us an idea of what are some properties of relations which we can identify and can start to kind of group relations by which properties they have and see which relations have things in common and which ones are different in some fundamental way. All right, so I'll say as a reminder, there's homework due today. Get that in this morning. There is a current homework up now due in a week. I'll be adding some more problems to that from the material we talked about today. If you have any questions, I can stick around for a little bit. In particular, I took attendance right at the beginning and some people showed up just a little bit later. If you showed up a little bit late, let me, or hold on a second so I can mark you present. Okay, got everyone. Great. So if you have any questions, I can stick around for a little bit. If not, try to keep up on the homework and I'll see you guys next week. Do any of you guys have questions you want to stick around for that I can answer? I want to make sure I don't log off and just leave you guys here unless, well, or if you wanted to ask me something. Nope. All right. Well, then I'll see you guys later.